Out there in the vast darkness of space, something is calling out to us, not with words, not with images, but with pulses of energy so strange and precise, they defy everything we know. Picture this: a signal bursts into existence, repeating like clockwork, echoing across the cosmos with no sender, no explanation, and no trace of its origin. It's not science fiction, it's happening right now, and it's one of the greatest mysteries of our time. These aren't just random blips on a radar, they're cosmic enigmas, whispering secrets that could rewrite our understanding of the universe itself. For decades, astronomers have trained their telescopes on the stars, listening for anything out of the ordinary, and what they've found is both thrilling and unsettling. Signals that repeat without reason, patterns that appear and vanish, and bursts of energy so powerful, they must come from something extraordinary. Some last mere milliseconds, while others pulse for years, taunting us with their consistency. The strangest part, no natural phenomenon we know of can fully explain them. Are they the echoes of dying stars, the signatures of undiscovered physics, or something even more unimaginable? The answers, or the lack of them, are what make these signals so endlessly fascinating. Today, we're diving deep into 20 of the most perplexing signals ever detected, messages from the void that refuse to reveal their secrets, from the infamous WOW signal that vanished without a trace to the eerie, repeating fast radio bursts that seem almost deliberate. Each one is a puzzle waiting to be solved. Could some of them be the work of intelligence beyond our own? Or are we witnessing cosmic phenomena so rare we've yet to even name them? One thing's for certain: the universe is far stranger, far more mysterious than we ever imagined. So let's begin this journey together, unraveling the signals that haunt science and ignite our curiosity. The truth is out there, and it's waiting to be heard. On a quiet August night in 1977, the Big Ear radio telescope in Ohio picked up something extraordinary, a signal so intense it defied all expectations. The data came in as a sudden, narrowband burst of radio waves, peaking at a frequency astronomers had long considered a prime candidate for interstellar communication. The signal lasted just 72 seconds, but its intensity was off the charts, so much so that the scientist who first spotted it, Jerry Amon, circled the reading on the printout and scribbled, "Wow." In the margin, a name that would stick forever. What made the WOW signal so remarkable wasn't just its strength, it was its precision. The frequency matched the hydrogen line, a natural radio emission that many scientists believe could be a universal calling card for intelligent life. The signal appeared to originate near the constellation Sagittarius, but follow-up searches found nothing. No repeat, no trace, no explanation. Decades later, it remains one of the most tantalizing mysteries in astronomy. Theories about its origin span the spectrum. Some suggest it was a natural event, like a comet's hydrogen cloud reflecting sunlight, though no known comet matched the location at the time. Others propose it was a one-time cosmic fluke, a burst of energy from a distant star, or an unknown astrophysical phenomenon. Then, of course, there's the possibility that lingers in the back of every scientist's mind. Could it have been a deliberate transmission, a fleeting hello from another civilization? What's most haunting about the WOW signal isn't just what we don't know, it's what it represents. A single, brilliant flash in the cosmic dark, gone before we could even begin to understand it. It's a reminder that the universe is vast, unpredictable, and full of surprises. Even today, with telescopes far more advanced than Big Ear, we've never heard anything quite like it again. Was it a cosmic coincidence, a natural anomaly, or something more? The answer, like the signal itself, remains just out of reach. Fast radio bursts are like the universe's most elusive fireworks, blindingly bright, vanishing in an instant and leaving behind more questions than answers. These bursts pack more energy than the sun emits in decades into a pulse that lasts just milliseconds, traveling billions of light years to reach us. What's even stranger, some of them repeat, not in predictable rhythms, but in erratic, unpredictable patterns that defy everything we know about cosmic explosions. Take FRB 121102, the first repeater ever discovered. Unlike one-off bursts that could be chalked up to catastrophic collisions, this one keeps coming back, flickering on and off like a celestial Morse code no one can decipher. Theories about their origins range from the plausible to the downright speculative. Magnetar's highly magnetized neutron stars are a leading candidate, with their intense magnetic fields capable of generating such violent energy releases. But even that doesn't fully explain the repeaters. Why would a magnetar fire off sporadic bursts over years instead of a single, catastrophic event? Then there's the more provocative idea. Could these be engineered signals? Some scientists cautiously point out that the burst's properties, like their precise frequencies, align with what we might expect from an artificial beacon. Imagine a civilization using unimaginably powerful transmitters to broadcast their presence across galaxies. It's a long shot, but in the absence of a natural explanation, even fringe ideas get a seat at the table. The plot thickens when you consider where these bursts come from. Many originate in dwarf galaxies, chaotic environments teeming with young stars and stellar remnants. These aren't the quiet corners of the universe, they're cosmic nurseries where extreme physics reigns. Could that environment birth phenomena we've never witnessed before? Or does the location hint at something else entirely, like a civilization harnessing the energy of their turbulent home? Every new detection adds another layer to the mystery. Some FRBs arrive with a side of persistent radio emissions, like an afterglow that lingers long after the initial burst. Others come solo, with no trace of what produced them. And then there's the mind-bending discovery that one FRB's repetition cycle matches a 16.35-day rhythm, a regularity that feels almost intentional. Nature rarely keeps time so precisely without a reason. What makes FRBs so captivating isn't just their mystery, it's what they represent. They're proof that the universe still holds phenomena we can't explain, even with our most advanced tools. Whether they're the screams of dying stars, the hum of alien megastructures, or something beyond our current physics, one thing's certain: these bursts are forcing us to rethink what's possible. And with every new flash from the depths of space, the cosmos reminds us how much we have yet to learn. Before fast radio bursts had a name, before astronomers even knew what to look for, there was the Lorimer Burst, a single, blinding flash of radio waves that rewrote the rules of cosmic phenomena. Discovered in 2007 by Duncan Lorimer and his team, this burst was unlike anything scientists had ever seen. Lasting just 5 milliseconds, it packed the energy of 500 million suns, all radiating from a source billions of light years away. What made it extraordinary wasn't just its power. It was the fact that, unlike later repeating FRBs, it never happened again. This one-off nature sent researchers scrambling for explanations. Could it have been the death cry of a collapsing black hole, a magnetar's final spin, or perhaps the collision of two neutron stars? Cataclysmic events like these might explain the burst's intensity, but they don't account for why we've never detected another like it. The Lorimer Burst stands alone, a cosmic anomaly that refuses to fit neatly into any existing category. Its discovery forced astronomers to confront a tantalizing possibility. What if not all fast radio bursts are created equal? Some might be produced by violent, one-time events, cosmic accidents that leave no trace. Others, like the repeating FRBs detected later, could stem from entirely different mechanisms such as magnetars or even, dare we say it, artificial sources. The Lorimer Burst didn't just deepen the mystery of FRBs, it shattered the assumption that they were all variations of the same phenomenon. Even the burst's location adds to the puzzle. Tracing its path back through the cosmos, scientists pinpointed its origin in a distant galaxy, far from the turbulent dwarf galaxies where many repeating FRBs are found. This disparity hints that the environments producing these signals might be as diverse as the signals themselves. Could there be an entire zoo of FRB sources out there, each with its own unique trigger? The legacy of the Lorimer Burst isn't just in the questions it raised, it's in the way it changed how we listen to the universe. Before it, no one was systematically searching for such fleeting signals. Afterward, telescopes worldwide began scanning the skies, eager to catch the next cosmic whisper. Yet, despite all our advances, the original burst remains an enigma, a fleeting reminder that the universe still holds surprises we can't yet imagine. What's most striking about the Lorimer Burst isn't just its power or its loneliness, it's the way it defies our hunger for patterns. Humans crave repetition. It's how we make sense of the world. But this burst refuses to oblige. It's a solitary note in the cosmic symphony, leaving us to wonder, was it a fluke or the first clue to something far greater? Until we find another like it, the Lorimer Burst will remain a ghost, a brilliant, unanswered question hanging in the dark. Canada's CHIME telescope isn't just another eye on the sky. It's a revolutionary machine built to catch the universe's most fleeting whispers. Since it began scanning the cosmos in 2018, it's turned the field of fast radio bursts upside down, uncovering a treasure trove of repeating signals that defy logic. Unlike the one-off bursts that vanish without a trace, these CHIME repeaters come back again and again, some with intervals so precise they feel almost mechanical. Take FRB 181214, for example. This burst doesn't just repeat, it does so in a 16-day cycle, firing off clusters of signals for 4 days before falling silent for 12. That kind of regularity isn't just rare in nature, it's practically unheard of. What makes these repeating FRBs so baffling is how they refuse to fit into any existing astrophysical playbook. Magnetars neutron stars with magnetic fields trillions of times stronger than Earth's are the usual suspects, capable of producing violent energy flares. But even the most extreme magnetar models struggle to explain why some bursts repeat like clockwork while others sputter out randomly. Could there be multiple types of sources at work? Some researchers speculate that younger, more active magnetars might produce erratic bursts, while older, stable ones settle into rhythmic patterns. Others propose even wilder ideas, like cosmic strings, hypothetical defects in space-time vibrating like plucked guitar strings to generate these signals. Then there's the location puzzle. Many CHIME repeaters originate in dense, star-forming regions, where the chaos of newborn stars and stellar explosions could provide the energy needed for such extreme bursts. But a few come from quieter, more isolated corners of the universe, where the environment seems too calm to produce anything so violent. This mismatch hints that FRBs might not have a single origin story. They could be the cosmic equivalent of fingerprints, each one unique to its source. The most tantalizing question, though, is what these repeating patterns might reveal. Nature rarely creates perfect rhythms without a reason. Think of pulsars, which emit radio waves with metronomic precision as they spin. But pulsars follow straightforward physics. They tick slow predictably over time. Chime repeaters, on the other hand, dance to their own tune, some speeding up, others slowing down, as if governed by rules we haven't discovered yet. Could these be natural cosmic clocks, or is there something more deliberate at play? Every new detection from chime adds another layer to the mystery. In 2021, the telescope spotted an FRB that not only repeated but also varied in brightness, as if its source were rotating in and out of view. Another exhibited downward frequency drifting, a subtle shift in pitch that suggests the signal is traveling through turbulent plasma, like a ship's horn fading as it moves through fog. These quirks aren't just curiosities, they're clues, tiny breadcrumbs that might one day lead us to the truth. What's clear is that chime repeaters are rewriting the rules of astrophysics. They're forcing scientists to rethink what's possible, pushing the boundaries of our understanding in ways no one anticipated. Whether they're the cries of magnetars, the echoes of cosmic catastrophes, or something beyond our wildest theories, these signals are a reminder the universe is stranger, more intricate, and more wondrous than we ever imagined. And with every pulse, every repetition, it invites us to listen a little closer. At first glance, the Puritans seemed like the perfect cosmic mystery, fast, bright radio bursts that matched the profile of distant astrophysical phenomena. Detected by the Parkes Observatory in Australia, these signals had all the hallmarks of extraterrestrial origin. They appeared suddenly, vanished just as quickly, and came from seemingly random directions in the sky. But in 2015, researchers stumbled upon a truth far more mundane and far more hilarious. The Puritans weren't messages from the stars, they were the hungry sighs of astronomers' microwave ovens. Here's how the mystery unraveled. Scientists noticed the bursts only occurred during daytime hours, and always when the observatory staff took lunch breaks. Digging deeper, they discovered that opening the microwave door mid-cycle, say, to check on a reheated meal, released a burst of radio waves at the exact frequency of the so-called Puritans. The telescope, incredibly sensitive to even the faintest cosmic whispers, had been picking up interference from its own cafeteria. The Puritans episode isn't just a funny footnote in astronomy history, it's a masterclass in scientific humility. For years, researchers had grappled with these signals, publishing papers and debating their origins, never suspecting the answer was literally under their noses. It underscores a crucial lesson. In the hunt for cosmic anomalies, the most exotic explanations are often the least likely. Before invoking black holes, neutron stars, or alien civilizations, scientists must first rule out the ordinary. This principle isn't just about microwaves. Across astronomy, false alarms abound. Radio interference from satellites, reflections off space debris, even glitches in telescope software have all masqueraded as groundbreaking discoveries. The infamous alien megastructure star KIC 8462852 later proved to be shrouded in dust, not Dyson spheres. Even the WOW signal, as tantalizing as it remains, could yet have a mundane explanation we haven't uncovered. What makes the Puritan story so valuable is how it reshaped the search for extraterrestrial intelligence. SETI researchers now employ rigorous vetting chains, cross-checking every candidate signal against every possible terrestrial source before crying alien. It's a painstaking process, but a necessary one. After all, the universe is under no obligation to make its signals easy to interpret. Yet there's a deeper irony here. The very sensitivity that makes modern telescopes so powerful, their ability to catch whispers from the edge of the cosmos, also makes them vulnerable to earthly noise. It's a double-edged sword. Without it, we'd miss the faintest, most distant signals. With it, we risk chasing ghosts in our own machinery. the Puritans remind us that science isn't just about discovery, it's about correction. Every false alarm, every dead end is a step toward refining our methods, and sometimes the most important breakthroughs aren't in what we find, but in how we learn to look. So the next time you heat up leftovers, remember, even the humblest human inventions can teach us something profound about the universe and our place within it. In 2020, the world held its breath as astronomers announced a signal unlike any other, a narrowband radio emission originating from Proxima Centauri, the closest star system to our Sun. Dubbed BLC-1, this signal seemed to tick all the boxes for artificial origin. It was concentrated at 982 MHz, a frequency conspicuously free of natural cosmic noise, and it drifted in a way that suggested a distant transmitter. Most tantalizing of all, it came from the direction of a star known to host at least one potentially habitable planet. For a brief, electrifying moment, the possibility of contact felt closer than ever. The story of BLC-1 is a masterclass in scientific caution. Discovered by the Breakthrough Listen project, which scans the skies for signs of extraterrestrial intelligence, the signal underwent months of rigorous analysis. At first glance, its properties were uncanny. Unlike the chaotic bursts of natural radio sources, BLC-1 was a pure tone, almost like a carrier wave, exactly the kind of signature you'd expect from a deliberate transmission. But as researchers dug deeper, cracks began to appear. The signal didn't behave like something traveling across interstellar space. Its drift rate was inconsistent, and follow-up observations failed to detect it again. Eventually, the culprit was identified: human-made radio interference, likely from a malfunctioning device or satellite right here on Earth. What makes BLC-1 so significant isn't just the false alarm, it's the way it exposed the needle in a haystack nature of SETI. The modern world is awash in radio noise, from Wi-Fi routers to cell towers to passing airplanes. Distinguishing a genuine cosmic signal from this cacophony is like trying to hear a whisper in a hurricane. Even signals that seem perfect narrowband, drifting, and originating from a promising star can turn out to be terrestrial imposters. This isn't just a technical challenge, it's a philosophical one. How do we stay open to the extraordinary without jumping to conclusions? The BLC-1 episode also highlights an uncomfortable truth: we may be looking for the wrong things. Traditional SETI assumes extraterrestrial civilizations would use radio waves, just as we once did. But what if they've moved beyond that? Advanced civilizations might communicate with lasers, neutrinos, or even quantum entanglement, technologies we're only beginning to grasp. BLC-1's false promise reminds us that our search is limited by our own imagination and technological infancy. Yet, for all its frustrations, BLC-1 wasn't a failure. It proved our detection methods are sensitive enough to catch whispers that could be alien. It also forced the SETI community to refine its vetting protocols, ensuring future signals face even more scrutiny. Most importantly, it reignited public fascination with the search for cosmic neighbors. In science, dead ends aren't dead, they're detours guiding us toward better questions. BLC-1 may not have been the signal we hoped for, but it taught us something just as valuable. The universe is full of surprises, and the next one might be real. So where does that leave us? Still listening, still wondering? The stars haven't stopped whispering, and neither have we. Every false alarm brings us closer to recognizing the real thing, if it's out there. And until then, the search continues, fueled by equal parts patience and possibility. After all, the greatest discovery in history could be just one signal away. When the Kepler Space Telescope turned its gaze toward distant star systems, it wasn't just hunting for planets, it stumbled upon something far stranger. Scattered among the data were bursts of radio energy, flickering signals tied not to stars or galaxies, but to specific exoplanets. Unlike the fleeting, high-energy pulses of fast radio bursts, these emissions were quieter, more localized, and eerily consistent with the orbits of their host worlds. The discovery sent shockwaves through the astronomy community. Why would planets, especially those light years away, produce radio signals at all? One leading theory points to planetary magnetic fields. In our own solar system, Jupiter's magnetosphere generates powerful radio waves as charged particles from the solar wind collide with its magnetic field. If an exoplanet had a magnetic field orders of magnitude stronger, perhaps a gas giant orbiting perilously close to its star, it could produce detectable bursts. But Kepler's signals don't always fit this mold. Some originate from smaller, rocky worlds where magnetic fields shouldn't be nearly as intense. That's where things get speculative. Could these planets harbor extreme volcanic activity or plasma-filled atmospheres creating natural radio beacons, or is there something else at play? The more provocative possibility, the one that lingers in the back of every researcher's mind, is that these signals aren't natural at all. Radio waves are a hallmark of human technology, from AM broadcasts to radar. If another civilization out there had developed similar technology, even centuries ago, their leakage could theoretically reach us. The idea isn't as far-fetched as it sounds. Earth's earliest radio transmissions, like the first TV broadcasts, have already traveled over 100 light-years into space. If an exoplanet hosted a civilization with even modest radio technology, Kepler might have caught their equivalent of a cosmic SOS, or just their version of static. Yet skepticism is healthy. The universe excels at producing phenomena that mimic artificiality. Pulsars, for instance, were initially nicknamed LGM-1, little green men, due to their unnervingly regular pulses, only to be revealed as spinning neutron stars. Kepler's radio bursts could easily be another cosmic red herring, a trick of physics we haven't yet unraveled. After all, nature doesn't need intelligence to create patterns. Magnetism, plasma dynamics, and even interstellar weather can produce signals that seem deliberate. What makes these bursts so compelling is their specificity. Unlike FRBs, which appear to come from random patches of sky, Kepler's signals align with known exoplanets' worlds we've mapped and studied. This correlation raises the stakes. If the signals are natural, they could teach us about planetary magnetic fields in extreme environments, shedding light on how exoplanets evolve. If they're not, well, that's a conversation humanity isn't ready to have. For now, the debate hinges on one critical question: how do we tell the difference? Future telescopes like the Square Kilometre Array may provide answers, scanning exoplanets for radio emissions with unprecedented precision. Until then, Kepler's bursts remain a tantalizing maybe, a whisper of something extraordinary, just beyond the edge of our understanding. Whether they're the cries of magnetized planets or the echoes of distant technology, one thing's certain: the cosmos is speaking. We're only beginning to learn how to listen. In 2016, the Ratan 600 radio telescope in Russia caught something extraordinary: a powerful, narrowband signal emanating from the star system, HD 164595. This wasn't just another blip in the cosmic static. The signal's intensity and frequency were so unusual, they sparked immediate speculation. Could this be the long-sought evidence of extraterrestrial technology? The star, located 94 light-years away, had already drawn attention for hosting a Neptune-sized exoplanet in its habitable zone, making the discovery all the more tantalizing. What set this signal apart was its resemblance to what scientists call a Type Roman II civilization signature, a hypothetical beacon from a society capable of harnessing the energy of its entire star. The idea wasn't entirely fringe. In the 1960s, physicist Nikolai Kardashev proposed that advanced civilizations might be classified by their energy use, with type Roman II civilizations building megastructures like Dyson spheres to capture stellar power. The Ratan 600 anomaly, for a brief moment, seemed to fit the bill. The signal's strength suggested a transmitter far more powerful than anything humanity could muster, as if something or someone had intentionally aimed a cosmic spotlight in our direction. Yet, as quickly as the excitement flared, it dimmed. Follow-up observations by the SETI Institute and other telescopes found nothing. No repeat signal, no corroborating data, just silence. The most likely explanation: earthly interference, a passing satellite, a military radar test, or even a glitch in the telescope systems. But the absence of a definitive answer left room for lingering questions. Why did the signal appear so perfectly aligned with HD 164595? And why hasn't anything like it been detected since? The Ratan 600 anomaly underscores a recurring theme in the search for cosmic signals: the challenge of fleeting evidence. Unlike repeating FRBs or pulsars, which announce their presence with clockwork regularity, some signals vanish before they can be studied, leaving scientists with fragments of a puzzle they may never solve. This ephemeral quality makes them both irresistible and maddening. They tease the possibility of discovery while refusing to surrender their secrets. But there's a deeper lesson here. The scientific process thrives on verification, on the ability to test, retest, and confirm. A signal that can't be replicated is, in some ways, as useless as no signal at all. It's a reminder that extraordinary claims require extraordinary evidence, and that the universe often guards its mysteries jealously. The Ratan 600 anomaly may not have been the breakthrough we hoped for, but it reinforced a critical truth. The search for cosmic companions is as much about patience as it is about technology. For now, HD 164595 remains quiet, its one-time signal fading into the archives of cosmic curiosities. But the questions it raised about how we interpret anomalies, how we rule out false positives, and how we prepare for the day a signal does return continue to shape the future of astronomy. The universe is vast and its whispers are rare, but every now and then it gives us a glimpse of something just beyond our grasp, reminding us that the greatest discoveries might still be waiting in the static. Some stars twinkle gently in the night sky, their light steady and predictable. Then there's Tabby's star, a cosmic rebel that flickers like a candle in the wind, dimming unpredictably by as much as 22% at a time. Officially known as KIC 8462852, this distant sun first made headlines in 2015 when astronomer Tabitha Boyajian and her team spotted its bizarre behavior in Kepler telescope data. Unlike ordinary stars, which might dim slightly when planets pass in front of them, Tabby's star plunged in brightness erratically with no discernible pattern. The variations weren't just dramatic, they were unprecedented, sparking a firestorm of speculation that ranged from the plausible to the extraordinary. At first, scientists scrambled for natural explanations. Could a massive swarm of comets, thousands strong, be orbiting the star, blocking its light in chaotic intervals? Or perhaps an enormous cloud of interstellar dust drifting between the star and Earth was to blame. Both ideas had merit, but neither fully accounted for the star's extreme dimming. Comets, for instance, would leave telltale infrared signatures as their icy bodies vaporized near the star, yet none were detected. Dust, meanwhile, should scatter certain wavelengths of light in predictable ways, but Tabby's star's light curves defied those expectations. The more researchers studied it, the more the mystery deepened. Then came the idea that electrified the public imagination: alien megastructures. Astronomer Jason Wright proposed that the star's erratic dimming could be caused by a Dyson swarm, a vast array of energy collecting satellites built by an advanced civilization to harness their sun's power. The concept wasn't pure science fiction. It was rooted in the work of physicist Freeman Dyson, who theorized in the 1960s that sufficiently advanced societies might construct such megastructures to meet their energy needs. If even a fraction of Tabby's star's light was being blocked by artificial constructs, it would explain the irregular, deep dips in brightness. The internet erupted with excitement, and for a moment, it seemed humanity might be on the verge of the ultimate discovery. But science thrives on skepticism. Further observations, including data from the Hubble and Spitzer space telescopes, gradually chipped away at the megastructure hypothesis. Detailed analysis revealed that the dimming affected different wavelengths of light unevenly, a hallmark of fine dust particles, not solid megastructures. By 2018, the consensus had shifted. Tabby's star's odd behavior was likely caused by an immense, uneven dust ring or a family of disintegrating planets, not alien engineering. Yet the star refused to be fully explained. Even now, its dips remain irregular, and no single natural model fits all the data. The legacy of Tabby's star isn't just in the answers it provided, but in the questions it forced us to ask. How do we distinguish between the truly anomalous and the merely unexplained? When does an extraordinary claim deserve serious consideration, and when does it cross into wishful thinking? This star became a case study in scientific humility, reminding us that the universe is under no obligation to conform to our expectations. It also revealed something profound about human curiosity. We're drawn to mysteries not just for their solutions, but for the way they stretch our imaginations. Today, Tabby's star still flickers, still defies, still captivates. It's a reminder that some cosmic puzzles resist easy answers, and that's what makes them worth studying. Whether it's dust, comets, or something we haven't yet imagined, this star continues to challenge us, and in that challenge lies its greatest gift, the relentless push to look deeper, think broader, and stay open to the possibility that the next great discovery might be hiding in plain sight, waiting for us to see it with new eyes. Deep in the heart of Australia's outback, the park's observatory, affectionately known as the Dish, has become ground zero for some of the most perplexing cosmic signals ever recorded. Among its many discoveries, one fast radio burst stands out not just for its power, but for its eerie predictability. FRB 180916 doesn't just repeat. It follows a 16.35-day cycle with near-clockwork precision, firing off bursts for roughly 4 days before falling silent for the next 12. This isn't the chaotic randomness of most cosmic phenomena. It's a rhythm, a pattern so consistent it feels almost deliberate. What could possibly explain such regularity? In nature, repeating signals usually trace back to orbiting bodies or spinning objects. Pulsars, for instance, emit radio waves like lighthouse beams as they rotate, their intervals slowing gradually over millennia. But FRB 180916's cycle doesn't match any known astrophysical mechanism. Magnetars neutron stars with immense magnetic fields are the leading candidates for FRBs, but even their most violent flares don't operate on such a strict timetable. Could this burst be tied to an orbital dance? Some theorists suggest a binary system, where a magnetar's eruptions are periodically magnified or obscured by a companion star or black hole. The 16-day cycle might then reflect the time it takes for the duo to complete their gravitational waltz. Yet even this explanation leaves gaps. Why would such a system produce bursts only during a quarter of its orbit? And why do the bursts themselves vary in brightness, as if the source is flickering in and out of focus? The more we study this FRB, the more it resists categorization. It's as if the universe is teasing us with a riddle wrapped in a pulse. Then there's the tantalizing, if controversial, alternative. Could this be something engineered? The signal's precision mirrors what we might expect from a beacon, a deliberate broadcast designed to catch the attention of anyone listening. While most scientists rightly caution against jumping to extraterrestrial conclusions, the possibility lingers, a quiet hum in the back of the scientific imagination. After all, if humans were to build a cosmic lighthouse, wouldn't we make it unmistakably regular? Park's other FRBs add layers to the mystery. Some repeat randomly, others in clusters, and a few, like FRB 180916, with bizarre consistency. This diversity suggests that fast radio bursts aren't a single phenomenon but a family of them, each with its own origin story. The observatory's role in unraveling these enigmas can't be overstated. Its location far from urban radio interference and its cutting-edge instrumentation make it one of the best ears on the planet for catching these whispers from the void. What makes FRB 180916 so captivating isn't just the puzzle of its rhythm, it's what that rhythm implies about the universe. Nature rarely creates perfect loops without reason. Whether it's the gravitational dynamics of unseen companions, the spin of an exotic stellar remnant, or something beyond our current physics, this burst is forcing us to rethink what's possible. And with every new cycle, every new pulse, it invites us to listen more closely, to question more deeply, and to wonder, what else is out there ticking away in the dark, waiting to be heard? Nestled in the quiet hills of West Virginia, the Green Bank Telescope is a marvel of modern astronomy, its colossal dish stretching wider than a football field, listening intently to the faintest whispers of the cosmos. Unlike other telescopes bombarded by Earth's radio noise, Green Bank sits in the heart of the National Radio Quiet Zone, a sanctuary where even cell phones are banned to preserve the purity of its observations. Yet despite this isolation, the telescope has captured something peculiar, signals that defy classification, pulsing through the void with no clear origin or pattern. These aren't the predictable ticks of pulsars or the explosive bursts of FRBs, they're anomalies, cosmic glitches that flicker in and out of existence like a radio station tuning itself in and out of range. One of the most baffling signals, dubbed GRB 701203, arrived without warning in 2019, a series of irregular pulses spaced days, then weeks apart. Unlike the rhythmic beats of a neutron star or the one-off crashes of a collapsing black hole, this signal danced to its own chaotic tune. At times, it vanished for months, only to reappear with renewed vigor, as if teasing astronomers with its unpredictability. The leading theory points to magnetars, those highly magnetized stellar corpses known for their violent outbursts. But even magnetars tend to follow rough patterns, their activity linked to the slow decay of their magnetic fields. GRB 701203 follows no such rules. It's as if the universe rolled cosmic dice to determine when it would speak again. Then there's the matter of location. Many of Green Bank's oddities originate in the so-called zone of avoidance, a region of space obscured by the dense dust and stars of our own Milky Way's galactic plane. Peering through this cosmic fog is like trying to spot a flashlight through a sandstorm, nearly impossible. Yet buried in the noise, Green Bank has teased out whispers that might otherwise have gone unheard. Could these signals be the distant cries of phenomena we've yet to name? Colliding neutron stars wrapped in debris clouds, rogue black holes ejecting jets of plasma, or even entirely new classes of objects lurking where our vision is weakest? The telescope's unique sensitivity makes it the perfect tool for uncovering these hidden voices, but with each discovery comes more questions than answers. What makes green banks detection so thrilling isn't just their mystery, it's their potential to rewrite the cosmic rulebook. Every unexplained signal is a breadcrumb, a clue that could lead to a breakthrough. Take the case of GB 158001, a faint, repeating pulse that shifts frequency unpredictably. At first glance, it resembles terrestrial interference, but its movement across the sky rules out any earthly source. Some researchers speculate it could be the signature of a wandering interstellar object, its magnetic field interacting with the galactic medium in ways we don't yet understand. Others suggest it might be the echo of a long-dead star, its remnants scattering radio waves like a cosmic funhouse mirror. The beauty of these oddities lies in their refusal to conform. They challenge astronomers to think beyond textbooks, to entertain possibilities that might once have seemed outlandish. And while most will likely have natural explanations, a quirk of plasma physics, a previously unnoticed celestial mechanic, their very existence reminds us how much we have yet to learn. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and telescopes like Green Bank are our best chance to eavesdrop on its secrets, one unpredictable pulse at a time. In 1974, humanity took a bold step into the cosmic unknown, not with a spaceship, but with a radio wave. From the massive dish of the Arecibo Observatory in Puerto Rico, scientists beamed a 3-minute message toward a cluster of stars 25,000 light-years away. This wasn't just random noise, it was a carefully crafted binary code containing information about Earth, our DNA, and even a crude illustration of a human figure. The Arecibo message was a symbolic gesture, a cosmic bottle tossed into the ocean of space, never really expected to reach its destination, let alone receive a reply. Decades later, whispers began to circulate that something extraordinary had happened. Anomalous signals detected by amateur radio enthusiasts seemed to mirror the original message structure. Could this be the echo we'd been waiting for? The idea electrified the public imagination, sparking debates and conspiracy theories. But the truth, as it often does, proved far more mundane. The echo was almost certainly terrestrial interference, a glitch, a satellite bounce, or even an unintentional replay of the original transmission. Yet the episode raised a profound question. If we ever do receive a reply from the stars, how will we recognize it as genuine? The challenge lies in the nature of cosmic communication. Space is awash with natural radio noise, pulsars, quasars, and the faint hiss of the cosmic microwave background. Amid this cacophony, distinguishing an artificial signal from natural static is like picking out a single voice in a crowded stadium. Even if an extraterrestrial civilization sent a deliberate reply, it might arrive garbled by interstellar plasma, stretched by the Doppler effect, or drowned out by Earth's own radio pollution. Then there's the problem of verification. A true extraterrestrial signal would need to pass rigorous tests. Is it repeatable? Does it originate from a fixed point in space? Does it contain mathematical or structural patterns that defy natural explanations? The Arecibo echo failed these checks, but future signals might not. Scientists have developed protocols like the Rio scale and the San Marino criteria to evaluate potential alien messages objectively. Yet even these frameworks rely on assumptions that extraterrestrials would think like us, encode information similarly, or even want to communicate. The Arecibo experiment, for all its symbolism, also highlights the fragility of interstellar dialogue. The original message was a fleeting pulse, a single shout in the dark. By the time it could conceivably reach its target, the star cluster M13 will have drifted out of alignment, rendering any reply impossible to detect. It's a humbling reminder that cosmic conversations operate on timescales far beyond human lifespans, and that patience is a prerequisite for anyone listening to the stars. What's most fascinating about the Arecibo message isn't the false echo or even the original transmission, it's the philosophical door it opened. For the first time, humanity confronted the practical challenges of talking to something beyond our world. The line between signal and noise isn't just a technical distinction, it's a mirror reflecting our own biases, hopes, and limitations. Every mysterious blip on a radio telescope forces us to ask, are we alone? And if we're not, how would we ever know? The Arecibo dish may now lie in ruins, its towering structure collapsed, but its legacy endures. It taught us that the search for cosmic companionship isn't just about technology, it's about interpretation, imagination, and the willingness to question everything. As newer telescopes scan the skies with ever greater precision, they carry forward this same mission: to listen, to wonder, and to stay ready for the day the universe might finally whisper back. Until then, the silence itself is a message we're only beginning to decode. In the summer of 1967, a young radio astronomer named Jocelyn Bell Burnell noticed something peculiar in the data from her telescope, a series of pulses so precise they seemed almost artificial. Every 1.337 seconds, like clockwork, a burst of radio energy arrived from deep space, ticking away with a regularity that defied all known natural phenomena. At first, the signal was jokingly labeled LGM-1, short for Little Green Men. The team half-seriously entertained the idea that they'd stumbled upon a beacon from an advanced civilization, a cosmic lighthouse built to announce its builder's presence to the galaxy. But the truth, when it came, was no less extraordinary. LGM-1 wasn't aliens, it was the first documented pulsar, a rapidly spinning neutron star the size of a city, but with the mass of a sun, beaming radiation into space like a celestial strobe light. As the star rotated, its intense magnetic fields funneled radio waves into narrow jets, sweeping across Earth with each spin like the beam of a cosmic searchlight. The discovery revolutionized astrophysics, proving the existence of these bizarre stellar remnants and earning Bell Burnell's advisor a Nobel Prize, though controversially, she herself was initially overlooked. What makes the LGM-1 story so compelling isn't just the science, it's the way it reshaped our approach to cosmic mysteries. Before pulsars, astronomers hadn't fully grasped how perfectly nature could mimic artificial signals. The realization that a dying star could produce pulses indistinguishable from a deliberate transmission forced scientists to rethink their criteria for identifying extraterrestrial intelligence. Suddenly, the bar for unnatural had to be set much higher. This lesson became foundational for SETI, the search for extraterrestrial intelligence, which now rigorously rules out natural explanations before entertaining even the faintest possibility of alien contact. Yet the pulsar's legacy goes beyond cautionary tales. Its discovery unveiled a whole new class of cosmic objects, neutron stars, whose extreme physics push the boundaries of our understanding. These ultra-dense remnants, born from supernova explosions, warp spacetime, spin hundreds of times per second, and harbor magnetic fields strong enough to shred atoms. Some, like the famous Crab pulsar, even power glowing nebulae with their relentless energy. LGM-1 wasn't just a false alarm, it was a key that unlocked an entire chapter of astrophysics, revealing how much wilder and more inventive the universe could be than our wildest speculations. Today, pulsars serve as more than just cosmic curiosities. Their impeccable timing makes them celestial navigation tools, helping spacecraft orient themselves in the void. Some are even being used to detect gravitational waves, the ripples in spacetime predicted by Einstein. And every new pulsar discovered is a reminder of that initial moment of wonder when humanity stood at the threshold of discovery, staring at a signal that seemed to say, "We are here, only to realize the universe had crafted something far stranger. The line between natural and artificial may be thinner than we think, but in that ambiguity lies the thrill of exploration, the promise that the next great signal might be hiding in plain sight, waiting for us to see it with new eyes. Among the many fast radio bursts that have puzzled astronomers, FRB 1905-20 stands out for one eerie reason: it never truly fades away. Unlike typical FRBs that flash brilliantly before vanishing into silence, this burst lingers, emitting a faint but persistent radio glow between its brighter outbursts. It's as if someone turned on a cosmic flashlight and forgot to switch it off, leaving astronomers scratching their heads over what could possibly power such sustained energy. The leading theory points to a magnetar in its rebellious youth, a neutron star with a magnetic field so intense it could strip the data from a credit card halfway across the galaxy. Young magnetars are known for their violent outbursts, and their extreme physics might explain both the bursts and the lingering afterglow. Imagine a stellar toddler throwing tantrums, each eruption shaking loose energy that lingers like the aftershocks of an earthquake. But even this explanation strains under scrutiny. Most magnetars don't produce FRBs, and none observed so far match 1905-20's combination of repetition and persistence. Then there's the location problem. This FRB hails from a dwarf galaxy over 3 billion light-years away, a small, chaotic environment where stars are born and die at a frenetic pace. Such galaxies are fertile ground for extreme cosmic events, but they are also messy, crowded with dust and plasma that could distort or amplify signals in ways we don't fully understand. Could the persistent glow be a side effect of the environment, like the echo of a shout bouncing between canyon walls? Or is the source itself something entirely new, a celestial object we haven't yet imagined, lurking in the cosmic shadows? The most tantalizing clue lies in the burst's behavior. While most repeating FRBs fire off randomly, 1905-20 follows loose patterns, with clusters of activity followed by eerie quiet. This inconsistency rules out simple mechanical explanations, like a spinning neutron star, and nudges theorists toward more exotic possibilities. Some suggest it could be a magnetar wrapped in a debris field, a stellar corpse shrouded in the remnants of its violent birth, with radio waves tunneling through the wreckage in unpredictable ways. Others propose a blitzar, a hypothetical ultra-dense object that briefly stabilizes before collapsing into a black hole, releasing energy in fits and starts. What makes this FRB so compelling isn't just the mystery, it's the way it defies categorization. In science, anomalies are gold mines. They're the cracks where new discoveries seep through. 1905-20 refuses to fit neatly into any existing box, and that's precisely why astronomers can't look away. Every new observation peels back another layer, revealing complexities that challenge our understanding of physics itself. Whether it's a young magnetar, an undiscovered celestial phenomenon, or something even stranger, one thing's certain: this cosmic oddball is rewriting the rules, one persistent pulse at a time. Fast radio bursts come in two flavors: the one-hit wonders and the repeat offenders. And strangely enough, the single bursts might be the most perplexing of all. While repeating FRBs like 12-1102 or 1809-16 offer scientists multiple chances to study them, the non-repeaters vanish after a single brilliant flash, leaving behind nothing but questions. What could explain such radically different behaviors from signals that otherwise look so similar? One school of thought suggests these bursts represent entirely separate cosmic phenomena. The repeaters might originate from magnetars, those hypermagnetic neutron stars capable of multiple eruptions, while the one-offs could be produced by catastrophic, one-time events. Imagine a neutron star collapsing into a black hole, or two ultra-dense objects like white dwarfs smashing together in a violent merger. These apocalyptic scenarios would release an enormous burst of energy, but the event itself would be so destructive that it could never happen again from the same source. It's the difference between a volcano erupting once in a cataclysmic explosion versus a geyser that spouts off periodically. But there's a twist. Some researchers argue that non-repeating and repeating FRBs might actually be the same phenomenon, just viewed at different stages or angles. A magnetar, for instance, could produce a series of bursts early in its life when its magnetic field is most unstable, then quiet down as it ages. From Earth's perspective, we might catch it during either phase, its fiery youth or its calmer maturity. Alternatively, the geometry of the burst could play a role. If a magnetar's energy beam is narrow, like a lighthouse focused in one direction, we might only see the signal if it happens to sweep across Earth. A repeater could simply be a source whose beam crosses our line of sight multiple times, while a one-off might be a beam that passes us once and never returns. The mystery deepens when you consider how many factors could influence what we detect. Interstellar plasma, the thin soup of charged particles between stars, can scatter and distort radio waves, potentially masking repeat signals that are too faint or smeared out to recognize. Some non-repeaters might actually be repeaters in disguise, their follow-up bursts too weak for our telescopes to catch. Then there's the challenge of observation time. Telescopes can't monitor every patch of sky continuously, so a burst that repeats every few months or years might slip through the cracks, mistaken for a one-time event simply because we weren't looking at the right moment. What makes this dichotomy so fascinating isn't just the scientific debate, it's what it reveals about our place in the universe. We're essentially cosmic eavesdroppers, straining to hear whispers from events that happened billions of years ago, often with incomplete information. Every non-repeating FRB could be a message in a bottle, a single, fleeting glimpse into a moment of cosmic violence we'll never witness again. And until we catch more of these signals in the act, or build telescopes sensitive enough to detect their quieter echoes, their secrets will remain locked away in the depths of space, tantalizingly out of reach. The absence of repetition might be the most telling clue of all. It forces us to confront how much we still don't understand about the universe's most energetic phenomena. Whether these one-off bursts are the death cries of exotic stellar objects or simply repeaters hiding in plain sight, they remind us that the cosmos is full of surprises, and that sometimes the most profound mysteries come in packages that vanish before we can fully unwrap them. The hunt for extraterrestrial signals is a story of tantalizing maybes, flashes of promise that flicker before fading into the static of cosmic noise. Over the decades, SETI researchers have flagged dozens of candidate signals, each one sparking a brief surge of hope before scrutiny revealed a more mundane truth. Take the famous SHGB 02+14a, detected in 2003, a signal that drifted in frequency just as an alien transmission might if originating from a planet orbiting a distant star. For a moment, it seemed to tick every box, but further analysis showed it was likely interference from Earth's own technology, a whisper mistaken for a shout across the light years. These near misses aren't just dead ends, they're dress rehearsals for the real thing. Every false alarm sharpens the tools and protocols scientists use to distinguish cosmic signals from terrestrial clutter. The modern SETI playbook includes layers of verification. Signals must be narrowband focused on a specific frequency, unlike natural cosmic noise, and they must drift in a way that suggests motion relative to Earth. Most crucially, they must originate beyond our solar system, ruling out satellites or space debris. Even then, the bar is set agonizingly high. A genuine alien signal wouldn't just meet these criteria. It would need to repeat, persist, and ideally carry some hallmark of artificial structure, a mathematical pattern or encoded information that nature couldn't produce by chance. Yet the challenge runs deeper than technical filters. Imagine an advanced civilization transmitting a signal meant for us. Would they use radio waves at all, or might they favor lasers, neutrinos, or some medium we haven't yet imagined? The infamous WOW signal remains the gold standard of unexplained detections precisely because it was a radio pulse, a technology humans understand. But what if other societies have moved beyond it? This uncertainty fuels SETI expansion into optical and infrared searches, scanning not just for deliberate messages but for accidental technosignatures, the waste heat of megastructures, the glow of city lights on exoplanets, or even the chemical traces of industrial pollution in alien atmospheres. The debate over what constitutes a genuine signal reveals a deeper philosophical rift. Some argue an unmistakable beacon like a pulse repeating prime numbers would be the only convincing evidence. Others contend that the first alien message might be subtle, even indecipherable, buried in noise we'd overlook without the right key. History offers a cautionary tale. When pulsars were first discovered, their precision seemed artificially engineered. Today, they're textbook examples of natural phenomena. The line between nature's ingenuity and extraterrestrial design may be thinner than we think. Despite the false starts, the search has never been more sophisticated. Projects like Breakthrough Listen harness the power of AI to sift through millions of frequencies simultaneously, while upcoming telescopes like the Square Kilometre Array promise unprecedented sensitivity. Each tool extends our cosmic ear further into the void, listening for a voice that might never speak, or might already be speaking, waiting for us to finally understand. What keeps SETI going isn't just the hope of discovery, but the certainty that not looking guarantees silence. Every dismissed signal, every dead end, is a step toward refining the search, stripping away illusions until only the truth remains. And if that truth is out there, hidden in the static of the universe, it's only a matter of time before we learn to hear it. Dark matter is the universe's greatest ghost story, an invisible presence that outweighs all visible matter 5 to 1, yet refuses to reveal itself. We know it's there because its gravity tugs on galaxies, bending light and sculpting the cosmos, but what it is remains one of science's most stubborn mysteries. Now, some theorists are asking a daring question. Could the strange, repeating signals from deep space, those enigmatic fast radio bursts and pulsar anomalies, be the first whispers of dark matter finally making itself heard? The idea hinges on dark matter's hypothetical particles. If they exist, they might occasionally interact with normal matter in ways we've yet to detect. One compelling theory suggests that certain dark matter particles, like actions or WIMP, weakly interacting massive particles, could cluster around dense objects like neutron stars. Under extreme magnetic fields, these particles might convert into radio waves, producing bursts that mirror the erratic patterns of FRBs. Imagine dark matter as a cosmic prankster, hiding in plain sight but occasionally slipping up, leaving behind radio fingerprints every time it brushes against the visible universe. Not all signals fit this mold, of course, but a few stand out. Take the bizarre case of pulsars that occasionally glitch, speeding up their rotation without warning. While most glitches are attributed to starquakes or sudden shifts in a neutron star's interior, some researchers speculate dark matter could play a role. If actions were drawn into a pulsar's crushing gravity well, their decay into photons might inject extra energy, nudging the star to spin faster. It's a stretch, but in the absence of definitive dark matter detections, even fringe ideas warrant exploration. Then there's the timing of certain repeating FRBs. If dark matter forms clumpy halos around galaxies, as simulations suggest, then signals passing through these regions might exhibit subtle distortions, like a radio echo or frequency drift. Astronomers have already noted oddities in some bursts that don't quite align with interstellar plasma alone. Could dark matter's hidden structures be the missing piece? Skeptics rightfully point out the lack of direct evidence. Dark matter's existence is inferred from gravity, not light or radio waves, and FRBs have plenty of plausible explanations, from magnetars to cosmic collisions, without invoking invisible particles. But the dark matter hypothesis offers something tantalizing, a way to kill two cosmic mysteries with one stone. If even a fraction of these signals trace back to dark matter interactions, we'd gain a revolutionary tool to study a substance that's eluded us for decades. The challenge lies in designing experiments to test the link. New telescopes, like the upcoming Square Kilometre Array, could analyze FRBs with unprecedented precision, hunting for telltale signs of dark matter's influence, anomalous scattering, unexpected energy distributions, or patterns that defy known astrophysics. Meanwhile, lab experiments here on Earth continue chasing actions and other particles, hoping to catch them in the act. What makes this idea so captivating isn't just its audacity, it's the way it reframes the search for dark matter. Instead of waiting for particles to hit a detector in a lab, we might already be hearing them in the static of space. The universe has a habit of hiding its greatest secrets in plain sight, wrapped in phenomena we're only beginning to decode. Whether dark matter is truly behind these signals or not, the possibility alone stretches our imagination, reminding us that the answers we seek might be lurking in the most unexpected places, even in the echoes of a burst we've yet to understand. Picture a civilization so advanced that it has outgrown planets, a society capable of dismantling entire star systems to build structures of unimaginable scale. This isn't science fiction, it's the heart of the alien megastructure hypothesis, a provocative idea that some repeating cosmic signals might not be natural at all, but the hum of machines built by intelligence beyond our own. The concept traces back to physicist Freeman Dyson, who theorized in 1960 that advanced civilizations could construct vast energy harvesting arrays around stars' swarms of solar collectors, now called Dyson spheres. These megastructures would absorb a star's light, re-emitting it as waste heat in the infrared spectrum. But what if, instead of just heat, they leaked something else, radio waves pulsing with the rhythm of their operations? The allure of this idea exploded in 2015 with the discovery of Tabby's star, a sun whose erratic dimming patterns defied all natural explanations. For a brief moment, the possibility of a partially completed Dyson swarm seemed plausible. While dust clouds eventually proved the more likely culprit, the episode ignited serious debate. Could other anomalies, especially repeating radio signals, be evidence of similar engineering? Fast radio bursts with clockwork regularity, like FRB 180916 16-day cycle, raise eyebrows. Nature rarely produces such precision without a mechanical cause. Even if the odds are vanishingly small, the hypothesis forces scientists to confront a radical question. How would we distinguish a natural cosmic heartbeat from the pulse of something built? Critics rightly point out the staggering energy requirements for interstellar engineering. Constructing a Dyson sphere would require dismantling planets, a feat beyond any technology we can envision. But proponents counter that a civilization millions of years older than ours might see such projects as trivial. After all, humans went from horse-drawn carriages to spaceflight in a single century. Who's to say what's possible given millennia more? And if such beings exist, their artifacts might not be monolithic spheres but fragmented swarms, their radio emissions flickering as they orbit, creating patterns we misinterpret as natural bursts. The real value of the megastructure hypothesis isn't just in its extraterrestrial romance, it's in how it reshapes our approach to cosmic anomalies. By entertaining even the most outlandish possibilities, scientists sharpen their criteria for what counts as evidence. Every strange signal is now scrutinized not just for astrophysical origins, but for subtle signatures of design, unusual spectral lines, unnatural periodicity, or energy distributions that defy known physics. It's a delicate balance, staying open to revolution without chasing fantasy. Perhaps the most enduring legacy of this idea is the way it stretches our imagination. The universe is 13.8 billion years old, plenty of time for intelligence to arise, evolve, and build on scales we can barely fathom. Whether any repeating signals trace back to such grandeur remains unknown. But the mere possibility reminds us that the cosmos is vast, ancient, and far stranger than our terrestrial minds might ever grasp. And in that vastness, amid the noise of collapsing stars and spinning pulsars, there might, just might, be something listening back. At the very edge of scientific speculation lies a theory so radical, it challenges our fundamental understanding of reality itself. Some physicists propose that certain cosmic signals, those inexplicable bursts and pulses that defy classification, might not originate from stars, black holes, or even alien technology, but from the fabric of space-time quivering at the quantum level. Imagine the universe as a vast, silent ocean, its surface seemingly calm, but peer closer, and you'd see it's alive with tiny, ceaseless ripples, quantum fluctuations where particles flicker in and out of existence in a dance of raw energy. What if, under extraordinary conditions, these microscopic tremors could amplify into detectable waves, sending shivers across the cosmos that register as phantom signals in our telescopes? This idea, while still firmly in the realm of hypothesis, emerges from the strange marriage of quantum mechanics and general relativity, two pillars of physics that stubbornly refuse to reconcile. In extreme environments like the edges of black holes or the seething plasma of the early universe, space-time itself might vibrate with enough violence to produce observable effects. Some researchers speculate that fast radio bursts could be the echoes of these quantum convulsions, space itself ringing like a bell struck by invisible hands. The math is tentative, the evidence circumstantial, but the implications are staggering. If true, it would mean we're not just detecting objects in space, but the very whispers of spacetime's quantum undercurrent. Critics argue that such effects would be too faint to ever reach our instruments, lost in the noise of conventional astrophysics, yet nature has a habit of surprising us. Consider gravitational waves, ripples in spacetime predicted by Einstein a century ago, only confirmed in 2015 when LIGO detected the collision of two black holes. Before their discovery, many doubted we'd ever measure such subtle distortions. Quantum spacetime noise, if it exists, might require even more sensitive detectors, or perhaps we've already recorded it without realizing. The persistent radio glow accompanying FRB 1905-20, for instance, doesn't neatly fit traditional models. Could it be the signature of spacetime itself settling after a quantum disturbance? What makes this theory so captivating isn't just its audacity, but the way it reframes our search for cosmic understanding. For centuries, we've assumed that every signal must come from something, a star, a planet, a craft. But the quantum noise hypothesis suggests we might be hearing the universe's background hum, the static of existence itself. It's a reminder that reality may operate on levels we're only beginning to perceive, with physics yet to be written. Until we can probe the quantum fabric of spacetime directly, these strange signals will remain either tantalizing clues or cosmic red herrings. But in either case, they invite us to listen more deeply, to question more boldly, and to embrace the possibility that the greatest mysteries aren't just in the stars, but in the space between them. After decades of scanning the skies with ever more sensitive instruments, the cosmos has responded with something unexpected, not a chorus of alien voices, but a profound and puzzling silence. This quiet is more than just an absence. It's a riddle wrapped in static, one that challenges our assumptions about life, intelligence, and our place in the universe. The famous Fermi paradox looms large here. If the universe is so vast and ancient, why haven't we heard a single whisper from another civilization? The answer might not lie in the stars themselves, but in the way we've been searching. Consider how briefly humanity has been listening. Radio astronomy is barely a century old, and systematic searches for extraterrestrial signals began in earnest only in the 1960s. Compared to the 13.8 billion-year age of the universe, our efforts amount to less than a blink of an eye. Imagine standing on a beach, scooping up a single grain of sand, and declaring the entire shore empty because you didn't find a seashell in that one tiny sample. That's essentially what we've done with the cosmos. Our search has been staggeringly narrow, both in time and space, limited to a handful of frequencies and a minuscule fraction of the sky. Then there's the question of what we're listening for. SETI has traditionally focused on radio waves, a logical choice given their ability to travel vast distances unimpeded. But what if advanced civilizations have moved beyond radio, just as we're transitioning from analog broadcasts to fiber optics and lasers? An alien society thousands or millions of years ahead of us might communicate using neutrino beams, quantum entanglement, or some other medium we haven't even discovered yet. Our reliance on 20th century technology could mean we're scanning the cosmic equivalent of a dial-up connection in an age of interstellar broadband. The silence might also be a matter of timing. Civilizations could be fleeting, their technological windows lasting mere centuries before they collapse, transcend, or self-destruct. The odds of two societies existing simultaneously and being close enough to detect each other might be vanishingly small. Earth, for instance, has been broadcasting detectable radio waves for only about 100 years. In cosmic terms, that's a flicker. If a civilization 1,000 light years away pointed their telescopes at us 200 years ago, they'd hear nothing but the rustling of wind and the calls of birds. But perhaps the most unsettling possibility is that we're simply not recognizing the signals that are already here. Nature is full of patterns that mimic artificiality, from pulsars to quasars, and an alien message might be hiding in plain sight, disguised as something else entirely. The mathematician Carl Sagan once speculated that advanced civilizations might encode messages in the very fabric of physics, constants like pi or the speed of light that appear universal but could contain deliberate anomalies. Until we learn to think like a species that's mastered the cosmos, we might be missing the forest for the trees. The next generation of telescopes, like the Square Kilometre Array and the James Webb Space Telescope, could shift the paradigm. With unprecedented sensitivity and the ability to scan millions of frequencies simultaneously, they might finally catch what we've been missing, or they might confirm the silence, forcing us to confront the haunting idea that we're alone, a solitary spark of consciousness in an endless, indifferent void. Either way, the answer will redefine humanity's place in the universe. For now, the silence isn't an end. It's an invitation to listen harder, think deeper, and stay humble in the face of the cosmos's grandest mystery. From the fleeting brilliance of the wow signal to the rhythmic pulses of fast radio bursts, these 20 cosmic enigmas serve as both a testament to human curiosity and a humbling reminder of how little we truly understand. Each signal, whether traced back to a collapsing star or still shrouded in mystery, peels back another layer of the universe's infinite complexity. They're not just anomalies, they're invitations. Invitations to question, to explore, and to admit that for all our technological prowess, we're still newcomers in a cosmos that's been unfolding for billions of years. Consider how far we've come. A century ago, astronomers debated whether the Milky Way was the entirety of the universe. Today, we're grappling with signals that cross billions of light years, each one a puzzle wrapped in plasma and magnetism. Yet for every answer, like the discovery that pulsars are spinning neutron stars, not alien beacons, we uncover 10 new questions. The repeating FRBs with their inexplicable rhythms, the eerie persistence of signals like FRB 190520, even the false alarms like BLC1 that teach us to refine our search, they all point to a universe far stranger than we've dared to imagine. What's next? The tools on the horizon promise revolutions. The Square Kilometre Array, slated to be the world's largest radio telescope, will scan the skies with such sensitivity it could detect an airport radar on a planet dozens of light years away. Machine learning algorithms sift through cosmic noise in real time, flagging patterns no human eye could catch. And projects like Breakthrough Listen are pushing SETI into new realms, searching not just for radio waves but for optical lasers and other technosignatures we've yet to conceive. The next great mystery might already be hiding in decades-old data, waiting for the right moment to reveal itself. But perhaps the most profound lesson these signals teach us isn't about astrophysics, it's about patience. The universe operates on timescales that dwarf human lifespans. A signal detected tomorrow might have been sent before Earth's continents took shape. And if we ever do receive a message, the civilization behind it could be long gone, their voices echoing across the void like whispers in an empty cathedral. That's the bittersweet beauty of the search. We may never know if we're alone, but the act of listening connects us to something larger than ourselves. So let these mysteries ignite your imagination. The next time you look up at the night sky, remember every star could be the origin of a signal we've yet to detect, or one we've misunderstood entirely. The cosmos isn't silent, it's speaking in a language we're still learning to decode. And with every breakthrough, every dead end, every tantalizing maybe, we're inching closer to understanding our place in the grand tapestry of existence. The greatest discovery might be just one frequency away. Until then, the stars keep calling. All we have to do is listen.